Today we are walking through incompressible knowledge probes estimating black box LLM parameter counts via factual capacity. The paper asks whether we can estimate the size of a closed language model by measuring how much factual knowledge it can store.
So the target is not benchmark score bragging. It is a way to infer hidden model size from what the model actually knows, right?
Exactly. Closed labs usually do not disclose parameter counts. The usual alternative is inference economics. This paper tries a more intrinsic signal factual capacity.
What makes factual knowledge useful for that? Models can compress patterns, so why would facts reveal size?
The key distinction is between procedural skill and isolated facts. A model can learn a better algorithm for reasoning, but it cannot derive the founding year of a small museum or the research area of an obscure scientist unless that association was stored somewhere.
That explains the intuition.
They build incompressible knowledge probes, or IKP 1400 factual questions across 7 tiers of obscurity. Easy tiers cover common facts. Harder tiers come from corpus-grounded sources such as Wikidata entities and researcher records. So the probes do not depend on an LLM inventing the questions from its own memory.
How are the tiers protected from being just popularity labels?
The paper assigns tiers empirically with the ladder of landmark models from small open models up to frontier systems. A probe belongs to a tier only if the corresponding landmark answers it and the previous landmark does not. Ambiguous probes that break this monotonic pattern are dropped.
Once every model has an IKP score, what is the actual size estimate?
They fit a log linear calibration on open-weight models with known sizes. Aggregate penalized accuracy is modeled as a linear function of the base 10 logarithm of parameter count. Then a closed model score can be inverted back into an estimated parameter count.
So the equation is not claiming exact size.
Right. The first major result is that the mapping is strong. Across 89 open-weight models from 19 vendors, IKP accuracy lines up with total parameter count within a squared of 0.917.
The dash closed model lines sit on the same scale as the open models.
Notice that the points do not form a random cloud. As known parameter counts rise from hundreds of millions to trillion scale systems, penalized IKP accuracy rises almost linearly on the log size axis. That is the evidence that long-tail factual capacity still scales with size.
Mixture of experts models complicates ICE claims. Do active parameters or total parameters better explain what facts they know?
The paper finds that total parameters are the better predictor. For MOE models, accuracy versus total parameters gets are squared around 0.79, while accuracy versus active parameters gets only about 0.51. The interpretation is that factual storage is spread across the experts, even when only some experts are active per token.
But if they fit in test on the same open models, could that curve just be overfit?
They check that with leave one out cross validation. For each open model, they refit the curve on the other 88 models and predict the held out size. The median error is 1.59 times. 68.5% of held out models land within 2 times their true size, and 87.6% land within 3 times.
That is useful, but it still has a wide uncertainty band.
Yes, the paper treats the estimates as effective knowledge capacity, not audited parameter counts. The important comparison is that this uncertainty is comparable to inference economics, while depending on what the model knows rather than on guesses about serving infrastructure.
What do the tier scores reveal beyond a single aggregate number?
The heat map shows a step pattern. Top models are basically saturated on universal and common facts, still separated on mid and deep tiers, and almost all of them collapse at the extreme T7 tier. That is why T3 through T6 carry most of the signal.
So T7 is not just harder.
That is the paper's interpretation. Only 2 models score above 1% penalized accuracy on T7, and every frontier proprietary model lands at 0% there. If factual capacity keeps scaling log linearly, the first strong T7 model would be a meaningful signal that the storage frontier has moved.
The paper also contrasts factual capacity with the idea that newer models get more capable at the same size.
They regress IKP accuracy against parameter count and release date for 96 dated open-weight models. If the same compression trends seen in reasoning benchmarks apply here, release date should add about 0.0117 accuracy points per month. Instead, the observed time coefficient is about minus 0.001 per month, statistically indistinguishable from 0.
That means procedural skills may compress over time, but the rare fact storage measure here does not show the same time discount.
Exactly. The strongest claim is not that every capability scales this way. It is now. Factual capacity continues to scale with parameters across vendors and generations, while reasoning style benchmark saturation does not imply the end of scaling.
The paper also mentions knowledge fingerprints. What does IKP measure there?
Rare facts are useful not only for capacity. The paper compares which T5 and T6 facts to models know, and also compares which wrong answers they produce when both fail. Shared wrong-rare facts are especially diagnostic because independently trained models are unlikely to hallucinate the same obscure wrong answer.
So the wrong answers are not just errors. They can reveal whether to release a share-based model.
Yes, the paper reports that weight-sharing siblings can match on 30 to 55% of shared wrong-rare probes, while independent weight trains are much lower. That lets IKP separate post-training updates from full rate range without needing model weights.
What does the paper say about why some facts are known and others disappear?
The paper argues for effective mention frequency. A fact is easier for a model to know when many training documents state that exact fact in a retrievable form, tied to the queried name or entity. Citation count, site links, and H-index are only partial proxies. Page views, practitioner adoption, named artifacts, and derivative documents often matter more.
Can you give one concrete pattern from those probes?
One example is the ML versus systems gap. In the researcher probes, low recognition systems researchers exist at very low citation counts, but the sampled machine learning researchers do not fall below 43% recognition. The paper attributes that to the denser ecosystem of blogs, demos, codecasts, and named artifacts around machine learning work.
And safety tuning can hide knowledge from this measurement, right?
Right. IKP treats refusals differently from hallucinations, because a refusal may mean the model knows something but will not answer. The paper notes that in one Claude-Sonnet comparison, the newer model reads 6.7 percentage points slower, while its T5 refusal rate jumps from 54% to 88%. That makes the estimate a lower bound for heavily safety-tuned models.
Why should we be cautious about the result?
There are several limits. The prediction interval is still wide. Retrieval-augmented systems could score high without storing facts and weights. API responses are not always deterministic, and safety tuning can hide knowledge by increasing refusals. The paper gives the Claude-Sonnet line as an example where a higher refusal rate can make effective capacity look lower.
So the result is strongest when we read it as a measuring instrument with uncertainty, not as a magic parameter counter.
That is the fair takeaway. IKP turns rare factual recall into a black box probe of model capacity. It cannot prove the exact number of weights, but it gives a grounded, repeatable estimate and shows that long-tail factual knowledge still grows with model size.
Got it. For closed models, the paper gives us a practical way to ask how much factual storage seems to be behind the API.
Exactly. That wraps up this paper walkthrough.